In this example, we're going to use the provisions in the ASCE7 standard to examine the seismic design category and response spectrum for a building site in Charleston, South Carolina. In this problem, we're going to consider a building site in Charleston, South Carolina, where the soil is characterized by a measured shear wave velocity of V sub s equal to 645 feet per second. We're going to determine the seismic design category for a risk category 2 structure on the site. We're going to sketch the design response spectrum for the site, and then we're going to estimate the design ground acceleration based on the idea of a steel concentrically braced frame or a steel moment frame constructed there. For this particular site in Charleston, South Carolina, we're going to take S sub s as 1.5 times G. We're going to take S sub 1 as 0.5 times G. And we're going to take T sub L equal to 8 seconds. These values come from the 2016 edition of the ASCE7 standard, Chapter 22. For a shear wave velocity of V sub s equals 645 feet per second, we can determine that the site would be classified as a site class D. And then based on that, we can look up the values of F sub A equal to 1.0 and F sub V equal to 1.8. The next step would be to calculate the values S sub ms and S sub m1. S sub ms is the product of F sub A and S sub s. We get 1.5 times G for that value. And S sub m is the product of F sub V and S sub 1, and we get 0.9 times G for that value. Next, we multiply by the value of 2/3 in order to go from the maximum considered earthquake to the design basis earthquake. So S sub ds works out to be 1.0 times G, and S sub d1 works out to be 0.6 times G. Next, we can determine the seismic design categories, both for a risk category 1, 2, or 3 structure, and then a risk category 4 structure. And as you can see here, in all cases, both based on S sub ds and S sub d1, the seismic design category for the site would be a D. The seismic design category for the structure would be a category D. Next, we'll look at the response spectrum for the site, and this is the form of the response spectrum without any values posted in. And then, of course, we can fill in the values. On the horizontal axis, we have T naught equal to 0.12 seconds, and then we have T sub s equal to 0.6 seconds. Then we have the 1 second period, of course, and then T sub L equal to 8 seconds. On the vertical axis, for the spectral acceleration, at the peak, we have a value of S sub A equal to S sub ds of 1 times G. Then we have the 1 second period acceleration, S sub d1 of 0.6 times G, and then the root of the sloping portion is 0.4 times G. To determine the appropriate spectral acceleration for our structure, we need to know what the period of our structure is. To determine that period, we're going to use the approximate period given in section 12.8.2 of the 2016 edition of the ASCE7 standard, where the approximate fundamental period is given as C sub t times h sub n to the x power. First, we're going to consider a steel concentrically braced frame with a height of 40 feet. And for steel CBF, we have a value of C sub t given to us as 0.020 and a value of x given as 0.75. Substituting into our equation, we find that we have an approximate fundamental period of 0.318 seconds. Going to our response spectrum for this particular site, we can see that for a period of 0.318 seconds, that corresponds to the peak of our response spectrum, and we would have a spectral acceleration for that structure on that site equal to 1 times G. Next, for a steel moment resisting frame with a height of 100 feet, we could see that C sub t is equal to 0.028 and that x is equal to 0.80. Substituting these values in, we find that for the moment resisting frame, the approximate period would be about 1.11 seconds. Going back to our response spectrum now for the moment resisting frame, at a period of t equals 1.1 seconds, we could see that we would have a spectral acceleration approximately equal to 0.55 times g. In fact, you could calculate the spectral acceleration exactly by taking s sub d1 divided by t. So for a value of 0.6 divided by 1.11, you would end up with s sub a equal to 0.541 times g. You may have noticed that there was a superscript on the value of f sub v from table 11.4-2 out of the ASCE 7 standard that indicates that a site-specific ground motion may need to be developed. However, per section 11.4.8, since our structure is on a site class D with S sub 1 greater than 0.2, a site-specific ground motion analysis is not required, provided that the value of S sub A is taken as S sub ds for cases where our period of our structure is less than 1.5 times T sub S, or provided that the value of S sub A is taken as 1.5 times the response spectrum value for a period T greater than 1.5 times T sub S. 1.5 times T sub S, in this particular case, is equal to 0.9 seconds. So we had an approximate period of 0.318 seconds for our concentrically braced frame. That's less than 1.5 times T sub S. So the value of S sub A is already taken as S sub ds for that case, the peak of the response spectrum. So this does not affect the value of S sub A for the concentrically braced frame. However, the approximate period of the moment resisting frame was 1.11 seconds. That's greater than 1.5 times T sub S for the moment resisting frame. So a spectral acceleration of S sub A equal to 1.5 times 0.55 or 0.825 can be used for the moment resisting frame in order to avoid the requirement of a site-specific ground motion hazard analysis. Thus, in order to avoid that ground motion hazard analysis, we would use a value of S sub A equal to 0.825 G for the moment resisting frame. Or you could pay a geotechnical engineer to do that site-specific ground motion hazard